Chapter 5, Torsion, Part B, Parallel and Series Concept in Beams and Shafts. Fundamentals of electricity. If you observe a parallel circuit condition, when you have a source of energy, a battery, connected to three lamps. In parallel condition, they share the same amount of voltage, mhm, but the current goes in each individual branch. So that's a 1/3 of I, that's 1/3 of I, that's 1/3 of current. But the total voltage or energy remains the same due to parallel condition. But the total current is the summation of the current in each branch. While in a series connection, when you have a source of energy connects a three lamps in a series condition. The same current passes through all the lamps. So in this condition, I remains the same, current remains the same in all of them, but the voltage is E1 plus E2. Total voltage is E1 plus E2 plus E3. That's E total. That's a series circuit. So again, I remains uh, the same for each of the lamps, but the energy is a summation of all those individuals. So that's E1 plus E2 plus E3 is E total. If we want to follow the same pattern, observe the same pattern in fluid mechanics, you can observe it in pipes in series and parallel. So in pipes in parallel, just assume you have a source of water, a discharge coming from the main stream and goes to a three branches of 1, 2, 3. In that case, discharge is divided by those three branches. A 1/3 of discharge passes through the first one, other the another 1/3 goes to the middle one, and in that sense, Q total is summation of the flow at each of those branches, while head loss between point A and B remains the same. So it doesn't matter how you get from point A to B. Head loss remains the same in pipes in parallel. While in pipes in series, if you have a discharge passing through a three different sections or pipe, the middle one, narrower one, and the widest section. So one can say the same amount of discharge passes through all the pipes. So Q or discharge remains the same all the way through the pipes, but head loss is a summation of HL1 plus HL2 plus. So one can say each of these pipe, due to their material and diameters, cross-sectional area, they can have different head loss. So if this is a steel and this is something like brass, they have different a coefficient for head loss, and they have different head loss. So total head loss is summation of all of them. If we want to connect the dot and see how that's related to mechanics of material, we can simulate our shafts and beam with different springs. So like one can say it's like I have K1, a spring K1, a spring K2, and a spring K3. as if they are representing three beams and fixed at two both ends, A and B, and as if a tensile force of P drags the configuration all the way to the right by the amount of delta to B prime. Mhm. And we do know force in a spring is Fs is stiffness of a spring times delta spring, and delta is delta. In that sense, if we can add these three springs with each other and replace that with a stronger K equivalent, mhm, one can easily see delta remains the same in each beam, shaft, or spring. Delta 1 is equal to delta 2, and all of them are equal to delta. Mhm. But the force inside each one, so and the amount of that delta is nothing but P over K, but this time P over total stiffness. So that's the total stiffness of the configuration. And force inside each beam, shaft, or spring is the stiffness for that member. So, for example, K1 over total stiffness times the total force. That's again beams and shaft in parallel configuration. And again, if we can replace them with a stronger spring, and that's our K equivalent, which is replacement of what we have all of the springs. And while in the connection in series, when you can have K1, K2, attach them in series and apply the force P by the amount of delta, and it just drags the system to the right again by the amount of delta. As you can see here, the concept like in beams, when a axial force applied to the one end of different blocks, separated blocks, and just drags all of them. So if there is no external force in each of them, so force remains the same in all of them. So P1 equal to P2 equal to P3, and that's equal to the same amount of force if there is no other force in between. And and again, you can simulate them with a K equivalent in series connection, and delta is summation, it's not remains the same. Delta is a summation of all deltas. Mhm. And again, delta in each member is 1 over the stiffness of that member over the 1 over the total stiffness times total delta. Mhm. Likewise, if we have this configuration, a force P applied at the center of two beams K1 or two spring K1 and K2 and pull the system by let the system to move, for example, to the right by the amount of zero point 0.2 inches. This is again a configuration of a parallel condition. Why? Because there is no other way. If K2 moves to the right by zero point 0.2 inches, the K1 has no other way to follow the same amount of delta. So if you remember, when delta remains the same, that's a condition of what? Of a parallel situation. Delta remains the same, but force is a summation of them. And force is, for example, P2. If P applies at the center of configuration, P2 is equal to a stiffness of the second one over total stiffness times the total P, and P1 is a stiffness of the first one over total stiffness times the total P in parallel connection. Likewise, in again in series, if you attach them like in this scenario in like like a train and apply the P at one end, that's a simulation of a series connection, while P remains the same and delta is summation of each individual delta. And delta is again, delta 1 here is 1 over stiffness of K1 over 1 over total stiffness time delta. Likewise, delta 2 is 1 over stiffness of second one over 1 over stiffness of total times total delta. And the point is, this approach is make the problem solving far easier, and we will observe that in a previous video, which I will upload the links for you here. Thank you.